No.
Like the 3x squared minus 3?
You sure can. I wrote it this way. Look, let's say you preferred that. That is totally fine. I want you, Josephine, or any student in here, to pick the one you find the easiest. What you find the easiest to plug into. If you're doing it mentally or if you're using a calculator. Okay? Just make sure you don't plug it into the original function. Is there ever going to be a time we plug something in the original function? Oh yeah. You'll see. In this list of them, there's some blanks in there. We're going to plug some numbers in the original. So we got to know that. That's the thing about Cal. You go, wait, oh, I plug in here. I plug in there. These are going in here. Now, who's got a number high on 1?
2.
All right. I'll use yours, Josephine. 3 times 2 squared minus 3. Positive or negative?
Positive.
Positive. Now I need a number over here. Negative 2.
Negative 2.
3 times negative 2 squared, which is positive, right? 12 minus 3. Cool. I like this one, but that doesn't mean every student likes this one to plug numbers in. You find the one that's the easiest, right? Whether it's the original or after you factored it. Just like we thought, everyone, didn't these signs keep alternating? Yeah, so expect that. Expect that. If you find one, you should see it, but I would double check a few of them. Don't assume they always went plus, minus, plus. Right? Now, look how many answers we got. First of all, I think with a pencil, could you just make a rough graph of what's going on here? Doesn't have to be perfect. If a function's got a positive slope, what would it do? So do it. Take your pen, like right underneath, I don't care how sloppy it is. Josephine, I don't care how sloppy it is. Just take your pencil right here and go, okay, the function was kind of going up here. And this is F. I'm driving it, I'm drawing a rough sketch of F here, right? All right, F went up. Then what happened from here?
Went down.
Oh, it went down. Now what happened to 1?
Going up.
Now I'm drawing F, so I do want to point out I know I got an F prime right there, but let me just put this as F. We know what to do now. Where is the function increasing? What intervals? Where are the pluses? Negative infinity to the
Negative 1.
negative 1. Is that the only part though?
No. Then
I'm looking at these pluses, right? Where else?
then union 1 to infinity.
Everyone agree? I'm just looking where I got my little pluses, right? That means the function was what? Going up. So I got to put a union and then put 1 to infinity. This is to make sure you communicate in this way. This is interval notation. You can keep all open parentheses. Don't worry about any closed brackets. And what do you do if you got more than one interval? Just put a union symbol. I don't think we're going to have a union symbol here, though. What do you get there?
This one, negative 1 to 1.
Looks like a point, but keep in mind, I'm going to put this word in front of it, and that's an interval. I didn't want you to think that's an XY coordinate. That's an interval. Does this make sense?
Mm-hmm.
I know you go, well, that's a simple function. But hey, if you can do it with this one, you can do it with them all. Now, I think we got this stuff. Everyone, look, which one of these is a local max? Which one's a local min?
So negative 1 is the local
You can
max.
see? And you did this for me. You were like, so you might do that to see which one's a local max. Absolutely, a local max is when the function goes from what? Increasing to decreasing. Some students, though, I get a kick out of this, and I don't get mad at them. They memorize. They go, okay, I'm going to memorize this. When I see plus to a minus in my F prime, that's a max. I mean, you could do that. I think it's more of what? Conceptual? You're like, oh yeah, it went up, and then it went what? Down. But yeah, students will do that. They'll show me their notes, and they go, look, professor, this is what I got. And they're like, okay, at any point, if it goes plus to a minus on an F prime like this, I know between a plus and minus, they go, this has to be a max on an F prime. And that's true, but that's what they'll memorize. I think it's more if you just make it conceptual in terms I understand it would increase and then decrease. So what's this number?
1.
There's a local max at negative 1. Cool. Now, where's the local min?
0.
Is it
No.
0? Oh.
No, 1.
Yeah, very good. Look, anyone see this? The function will what? There you go. Local min right there. So you got a local min right here. You got a local max right there. Cool? So I'll put this.
Does it always correspond with the critical point?
Yep. But, hey, Josephine, let me be careful. Sometimes you might get 3 or 4 critical points. It doesn't mean all 3 or 4 you have to fill out all your local max mins. One of those may be a point of inflection. Okay? Maybe or may not be. I just want to point that out. But the absolute essential test for points of inflection, Josephine, has to be through second derivative. But I just want to make you aware that sometimes a critical point is one of your points of inflection.
It's also when
You
you
know?
solve equals zero.
That's right. That's right. Now, everyone, this is interesting. So far, so good? Are you sure everyone okay with this?
Mhm.
All right, here we go. I've been plugging everything into what so far?
First derivative.
Look at these blank spaces. In the wording I have here, I'm saying how there was a local max of the function. At x equal -1, there's a local max of the function, and then I said the word is. If I'm talking about I'm talking about the y value of the original function. Guess where I gotta plug these now to fill in these?
Original function.
I'm going to the original. Alright, so I know everyone, that's where sometimes this stuff can get confused, like, what the heck's going on? He was just plugging things in here. But if I'm putting this word is, and I'm talking about the actual max of the actual function, I'm putting it all the way back in, way up here, right?
Mhm.
Way up there, that's to get these. Does that make sense? So let me just see, what's -1 cubed minus 3? 2?
Negative
I
one
get
plus
negative.
3. 2, it's 2.
-1 plus 3, 2?
Yeah, so
Good
negative
job,
1
everyone. I apologize, that's right. Now I want you to plug a 1 in here.
local mean.
Plug in the original. By the way, if you accidentally plugged it in here, I'll tell you what you'll get every time, zeros. Does that make sense? If you accidentally plugged it in here, you're getting slope of 0. Right? But it goes in the original. So this point right here was the point what? Oh, that was -1, 2. What was this point?
2, 6.
We got a great sense of this graph right now, everyone. At -1, it got up to what? 2, and then over at 1, it got down to what? What was it going at 1? It got down to what? -2, this is one of those snakes, right? Anybody know how to get a y-intercept in math? Just set x equal to 0. What's 0 minus 0? Why do we need a pre-calc class? Think about it. Remember when you had to build graphs in pre-calc? They talked about multiplicity and all this stuff? They're like, man, just do this stuff. That's a nice pretty graph, isn't it? Cool. Hey, let's keep going though. By the way, as you look at this image, you might already sense if there's any points of inflection. You see any concavity changing in there?
Yeah.
Can anybody, raise your hand, can you predict how many points of flexion we'll have? Just look. Look for between the cup and the upside down frown. How many do you see, Ben?
1.
Brilliant. And when he's saying there's only 1. Because I see, look, upside down frown. And then over here I see the what? Concave up. Right? And somewhere, and we do it left to right, Josephine. So somewhere between the what? The upside down frown and the cup. It looks like there's a point of frown. Where do you think it's happening? Where do you sense that probably there's a point of inflection?
At the x-axis.
Doesn't it look like it?
Mhm.
Y'all agree that's where it changed from the concave down to the concave up? Halfway between this max and min location, right? I think we're gonna be right, but what's the absolute test? This what? Second derivative stuff. So I'm about to erase this. You okay with that? Alright, it's getting wiped out. Except for one thing. That thing. Are you sure? Don't need the cell phone in? You got it. Now, what are we doing to get these answers? Second derivative test. Alright, so what's the second derivative?
6x.
You know what we set it equal to? 0 already? Oh, dude, or doesn't exist. That comes up. Look it up. So second derivative equals 0 and you solve for what? X. And if 6x equals 0, I'll divide a 6 on both sides. What's 0 divided 6?
0.
Now, let me tell you what this is. Be careful with this. Sometimes students make little mistakes. You know what? They think, here's what they go. Oh, a second derivative is where the a point of inflection is where the second derivative equals 0. Not exactly. This is called a possible point of inflection. We'll define it. What word do I have up there?
Possible.
I didn't want you to think, everyone, every time you just set second derivative equal to 0 and you get numbers, that they're points of inflections. They're all possible points of inflection. So what's the true definition of point of inflection? We'll go back to what we said earlier. It's where the second derivative does equal 0, but also it's where the concavity must change. Do you hear me? So there's only one way to make sure the concavity changes here. Right now it's just a possible point of inflection. We got to make another number line. And we're not going to call this the first derivative test. We're going to call this the what?
Second
The
derivative.
second derivative test, okay? That sound good? We can call it the second derivative test for concavity, how about that? Yeah, how about that? The second derivative test for concavity.
Wait, so does the second derivative always equal 0 for the points of inflection?
No,
Well, it will have to equal 0, but something else has to happen. That's true, but there's something else. The concavity must change. Okay? So what I'm saying is, let's say you and I, Josephine, we found 3 values where the second derivative equals 0. Maybe not all 3 are points of inflection. We have to go to this number line here, and we gotta analyze it to make sure concavity changes. Okay? Cool. So, everyone, I want you to list all your points of inflection on this number line. How many were there?
just
Possible points of inflection. Alright, here it is. You go, why can't we call these critical points? That term's already been taken. That's where the first term equals 0. So we call these not points of inflection, but what? Possible points of inflection. Now I'm gonna bracket this off. And when I like to rewrite the equation, this time Josephine only got one option, just 6x, right? Alright. Now I need some test points. What's an easy
One.
test point over here? 1?
Yeah.
Alright, 6 times 1, I don't care about the number, Sarah. Just, is it positive or negative?
positive.
Positive. And then, what's the test point over here? How about
Negative.
-1? Alright, I don't care about the number.
Mm,
Positive or negative, I plug a -1 in there. It's what?
Negative.
Negative. Now, since it's second derivative, let me go back to this. Shh. Shh. You remember these images?
mhm.
Well, what's gonna help us know about this stuff? This is concave up. F is concave up. And on a graph like this, F is what?
Concave down.
Concave down. Feel free to write CU and CD to abbreviate.
Mhm.
Something interesting going on with second derivative. The
In-
second derivative will be
Increasing.
negative.
Negative, sorry.
Oh, excuse me, on this, positive.
Uh-huh.
Over here, second derivative will be
Negative.
negative. Second derivative will be positive when it's concave up. Second derivative will be negative when it's concave down.
Yeah.
Cool.
The opposite thing?
Always. So I always want you to think with this thing, Josephine, it's the concave up, you know, second derivative must be what? Positive. And you go, why? Why is it positive? Because the slope of the tangent line to the curve is always increasing. If that makes sense.
You just said it. Follow my title.
Yeah, exactly. So, everyone, where's the concave up?
So concave is when it's positive, so that's
0
0 to
to-
infinity.
Alright, where was it concave down?
Negative infinity to 0.
Then what if you want to make little images in here? You can make like a cup like this. And then here you can make a little what? Upside down crown if you want. But that's what's probably going on with the graph, you see it? Josephine, did it change concavity?
Yes.
What I mean is the signs would have to change. So is that a point of inflection?
Mm-hmm.
Now hey, think about this. What if it went minus minus? That would not be a point of inflection, you follow me? Does that make sense?
Mm-hmm.
You bet, everyone. If this thing went low, minus minus. Now students in here might go, can you show me an example? I'll be glad to, a real simple one too. But it's a point of light because it changed from negative to positive. It changed from concave down to concave up. F is concave up. And then when I'm saying this, I have to be careful with my wording. I know I abbreviate up here. I'm saying F is concave up and F is concave down, but we use second derivative to find these answers. Now, for this, can't we just say this? X equal to 0? If you used WebAssign, you would have to put the y value with it, like an xy coordinate. Everyone, I'm okay if you just list the x values for points of inflection. Does that sound good? I'm serious, you just tell me the x values. But if you use WebAssign, so it would make you put the x and the what? And the y, okay? So Art, I'm okay if you just, when it comes to points of inflection, if you just say it occurs at x equal to, and just put the value.
Okay.
Cool. Oh, great job with this. Can we do another? Can
Sure.
we blast through everything? All I can do is erase all those spaces. Look, I'll leave this up here. I'll take that off, that off, that off. Isn't that cool? Look at all the stuff you know about this graph. Make a beautiful graph. You can answer all these questions. Cool? Yeah?
You're doing one more?
You ready?
Yes, sir.
All right. this one's coming up, everyone. Oh, and before I do it, I apologize. I wanted to show you one image. Remember execute? You can sell what? Hey, who in here thinks it's a good idea maybe even to look at some of these graphs on a calculator before you start? That's up to you. Just get a sense of where maybe you might have a what? Point of inflection? That's why that tool's there to support you, okay? But you'll be able to create everything. I wanted to show you something. X to the 4th. Now, did you know that graph looks just like x squared?
Mhm.
Okay? So watch what would happen. Let's say I'm looking for points of inflection. So I'm going to blast through the first derivative. I don't care about the first derivative. First derivative is 4x cubed, right? This is what I'm concerned about, everyone. What's the second derivative?
12x squared.
All right, check this out. Everyone, solve for x. I'm in the second derivative. Just when we were talking about the definition of points of inflection, we said points of inflection, the second derivative must equal 0 at those values. Or lightly in parentheses, I say, or it does not exist. But it doesn't guarantee it's a point of inflection, right? Something else must be true. Second derivative must be equal to 0 or it does not exist. And the concavity must do what? Second derivative must change signs.
Sign,
So,
yeah.
look at this. What's the value? What solves that equation? X equal to what?
0.
So right now, this is not a point of inflection, this is called a what?
Possible.
Possible point of inflection. And you'll notice something, look. My second derivative test. Anyone want to go? I mean, look at this. What's going on either side?
Both are positive.
It's positive over here. You put a negative in there, it's still what? Are there any points of inflection on that thing? Because this graph looks like what? What's it behave like?
Isn't that the same as x squared?
Yeah. Do you see any points of inflection? That's why, look what's happening. There are no points of inflection. It's always concave what? It's always concave up. Do you follow me? So that's why I wanted to show you that you go, oh, I'm going to make